So we're now about to begin a session featuring a number of talks on new technologies, new developments in the use of ultrasound for imaging. And our first talk is pulse echo medical ultrasound imaging based on Fourier image reconstruction. Jian-yu from the University of Toledo. Thanks very much.
So as we know, conventional pulse echo ultrasound system is done by focusing a beam, very narrow beam, in the direction people want to look, and use delay in the sound algorithm when the echoes come back to reconstruct images. That's currently done in almost all the medical imaging, ultrasound imaging machine in hospital. So today we are going to talk about a little bit different approach. So first we use a wider beam instead of focused beam, looking into a very small region or direction, but illuminate a large area. So the advantage of this is to get a higher image rate. Just like a flashlight, if you use a focused light in your camera to illuminate a small area, to take a picture of this room, probably you need to have multiple illumination. Each time get a small section of images and then piece them together. However, you use a current flashlight, usually it's broad beam. So once it's a flash, the entire scene is illuminated. So in this way, you don't need to do many times to compose an image. So that increases the frame rate. So two things. One is we use broad beams and to get a high frame rate. Another thing will be how we reconstruct images. Today here, we are going to talk about not using the delay in the sound image reconstruction, which is usually used in the hospital ultrasound machine. We use Fourier-based algorithm, which have the potential to increase speed of image reconstruction and get better images. That's why we think have a future in the ultrasound imaging. So how this was started? First, we started X waves. So what's X waves? X waves are a class of waves that are solutions to linear equations and do not spread as they propagate to infinite distance in theory. They have the same group velocity, which is the envelope of the wave, and the phase velocity. That is greater than the speed of sound or light in theory. That's only in theory. This is the X-ray formula. You can see the waves consist of the propagation terms, which is propagation invariant. So that means as the z distance increase, as well as time increase, this term will be fixed. In terms of this function X-ray, it doesn't change in the propagation. Because the function is a function of radius as function of angular direction, as well as the term. The term is a subtraction. So the wave will be propagating at a speed c1, which is calculated here. They are the same. It's c divided by cosine theta. Theta here is the hexagon angle. This is a transducer we made to produce this X-ray in water. And we designed the transducer in 10 rings. And using 1,3 polymer composite material to make a 10-ring annular array transducer. The size of the array is about 5 centimeters. This is the X-ray we produced in water. Here's the transducer. So as it propagates, you can see the size is about 25 millimeters. The weight is around 2.5 megahertz. And after propagating 170 millimeters, it keeps the same shape as it's on the surface of the transducer. And propagating to 340 millimeters, it keeps similar central lobe shape. This is a simulation on the top and experiment on the bottom. You can think about X-rays like a baseball type of object. Once it's projected, it's going straight line and keep on going. Based on the X-ray theory above, and we developed a high frame rate imaging method. What's the high frame rate imaging method? It constructs pulse echo images in Fourier domain, where the fast Fourier transformation, instead of traditional delay in the sum algorithm, can be used. And also obtain a better image quality in theory, since it's based on a more rigorous mathematical relationship. And it may reduce the computation thousands of times in three-dimensional imaging using fully sampled 2D arrays as compared to conventional delays in the sum imaging method. The procedure of this imaging, first we transmit collimated beams, such as a plane wave. Or you can use limited diffraction array beams. However, beams of small diverging angle, say 15 degrees, that's quite big already, or less, can be used quite satisfactorily also, just using the same image reconstruction algorithm, but just increasing the diverging beam divergence from 0 degree for plane waves to, say, around 15 degrees, the image still looks good. And then after we get the data using the array transducer, and we do the fast Fourier transformation of received signals over transducer aperture. That's a spatial Fourier transformation. Or we can weight the received aperture with limited diffraction beams. Either way, they are identical mathematically. And as well as we do the Fourier transformation over the time axis. So each signal received from each element of transducer is a time signal. So you can do Fourier transformation of that signal. And then you map the echoes in Fourier domain of the object, in the echo Fourier domain to the object Fourier domain. So object of Fourier domain is the Fourier transformation of that object you are going to look at, say, heart. The heart is a 3D image. You can do Fourier transformation. That Fourier transformation is called object Fourier domain. And the echo Fourier domain is doing the Fourier transformation of the signal you received from a 2D array transducer. Of course, for 1D, it's a special case. Then you get two-dimensional images. And then you reconstruct a two-dimensional or three-dimensional image with a single or multiple transmission using inverse Fourier transformation to get the object, to reconstruct the object. In the multiple transmissions means you can transmit multiple plane waves, or you can transmit multiple diverging waves, or transmit multiple limited diffraction beams. Then we can use masks to reconstruct the image and superpose them coherently to enhance image resolution, or incoherently to improve the contrast, spectral contrast for final reconstructed images. This is the illustration, just show you if you have a two-dimensional array, here's the three-dimensional object, you put a pulse, illuminate the object with a pulse, and get echoes, and each individual element are isolated, so you can have a signal from each transducer element and do the processing we just mentioned. And then to reconstruct the image. You can steer the transmitter beam in different directions. And to reconstruct the image of a larger field of view, and also at the same time, you get a higher image resolution. And the extended high frame rate imaging method is the same as the previous one we just mentioned, just use multiple transmissions. So here, for example, if you use plane wave, you eliminate like a coordinated area. This area is limited because the plane wave have zero divergence. So in order to construct the image of larger field of view, say you use a transducer peep into the windows between the ribs. And transducer size usually like 2 centimeters. So you can construct the image one at a time with centimeters width. That's not enough to see the entire heart. To see the entire heart, you would like to see wider areas. And if you use a little bit divergent beam, then you can use fewer transmissions to see the entire heart. But if you use plane waves, you can see a narrower area, and then put them together and then get an entire larger field of view composed images. This is the mapping we talk about in the Fourier space. Once we get echo Fourier domain signals and do the Fourier transformation, it's going to be fill up the space in the Fourier space in this shape. And then you map it to the object Fourier domain. And then do inverse Fourier transformation, you get images. That's with a limited diffraction array beam. But if you use a plane wave, then you get this area. And then you map into the object Fourier domain, and then you reconstruct the images. We also make a homemade imaging system to reconstruct images of human beings, as well as from phantoms. This is a system we bought like $20, a big equipment rack, and then pull out all the old equipment, and then put our own devices and electronics inside the boxes. And use computer, we develop an interface of this imaging system to control the system. And here is a transducer probe. Here's a phantom, which we can see what we are reconstructing and how well we reconstruct the images. Use the method which I just mentioned. So here's the transducer on top, and this is the object. I'm going to show you some videos here. So we designed a system . So this is an 8-layer board with 8 channels of receiver and a transmitter. They are all surface mounted devices. Put them together. Students in the lab and put these tiny, very small capacitors and the resistors, just solder them one by one into the board. And each FPGA have a couple hundreds of leads in a very small areas, so students just saw them like each one in a couple minutes. These are FPGAs. They line up. Each FPGA controls one channel. We have 128 channels in total. These are analog amplifier and FPGAs, and back on the digital memory systems. So students are happy after completed. We developed a software system to control all the FPGAs on the board and communicate the systems via the high-speed USB 2 connections. So those are the state machine in order to control the entire machine systems. And also we have ECG gating for the entire systems. So all those are the circuit design, multi-channel systems to see the digital logics. This is the whole system. This is the ECG machine. You can look inside what's inside. We have lots of power supply, different high voltage power supply as well as low voltage, high current power supplies. So these are the heatsink, big heatsink for the power supply. And we have to put this rack by rack couple of thousands of wires, put the entire system together. After the system is completed, we do the testing to make sure every part is working the way we designed. These are completed boards, you can see, and then use digital logic analyzer. We have multiple boards. So let's see some of the results. We put a few wires. Say here 7 wires, 1, 2, 3, 4, 5, 6, 7 in water, and use the transducer and the system, which I just showed you, to make images. And then we do the comparison. So if we use one plane wave to transmit, and then we use Fourier reconstruction, we get these images. If we use 11 transmissions, we get this image. Use 19, get this image. Use 91, we get these images. 91 transmission. But with the conventional focused beam, we can focus here and then diverge in other distance, and then refocus to this distance, and cut a piece of image put here, and do 1 by 1, do 6 times. And each time we use 274 transmissions to reconstruct images. Then we get a result similar to this with this 91 transmission, which uses plane wave, and also use Fourier transformation to reconstruct images. So they are very similar, but this has an advantage, as I mentioned before. And this is the phantom which I show you in the water tank. Now this is a closer look, and there's a pattern object inside this phantom. This is a dimension that we can make image in this area as well as make image in this area. Then we can compare the images. This is use 1 transmission, use Fourier reconstruction 11 and 91. And then we can use 279 transmission to focus in these depths. So you can see the focused beam, once it's focused here, you get a very good image reconstructed around the focus. But outside the focus, it tends to diverge. But with this 91 transmission, use plane wave, use Fourier reconstruction, we can get quite good images over the entire field of view. And we also see the images in the cyst area, the other area, in the horizontal direction. Then we can see these holes to see the contrast. Then use 91 transmission as compared to the conventional delay in the sun with 279 transmission focus at this depth. You can see out of focus, of course, image is not good, but around the focus is quite good. But in 91 plane wave transmission, you can get quite nice images, as well as you can see images just very close to the surface of transducer. But with delay in the sun, it's hard to see. This is the images we make for the kidney of people. This one uses 91 transmission, and this one uses 88 transmission, use delay in the sun image. So this is just some of the in vivo results, as well as use this imaging system for the heart. And we can see the heart images with 11 transmission, 19, and the 91 transmission as compared to the 88 transmission with delay in the sun method, which focus here. You can see outside the focus, the image tends to be a little bit fuzzy because of the nature of the focused beam. And use the 91 transmission, it looks like that. And also we can use limited diffraction array beam instead of plane wave to reconstruct the images. And here, the advantage of using that is we could use a square wave aperture weighting for transmission. The advantage is we can use 1 or 2 transmitter, linear power amplifier, to eliminate all the transducer element at the same time. So you don't need to have 1 channel per transmitter. This will save a lot of electronics. In the future, entirely fully sample the 2-dimensional array imaging. So what we do is array beam is more like this oscillating type of aperture weighting. This is a transducer aperture dimension. It's not in the time dimension. Then aperture weighting to produce those images. And we can use a square wave, just one negative use 1 level, 1 positive use 1 level, voltage level. Then we can construct the image, and only need 2 in this 1 or 2 transmitters to serve all the thousands of transmitter transducer elements. So this is the image result. You can see with the 11 transmission, use the exact limit diffraction array beam weighting, or use square wave weighting. You can see the image quality almost identical. And for 91 transmission, give you similar result. You can also see with this Fourier method, these are all constructed by the Fourier method. And with limited diffraction beam, you can see very close to the surface of transducer. Here's the surface of transducer. All the objects are clearly legible. And this is the sister images as well as the targets here. You can see they are almost identical. And we do the program our machine in such a way we transmit the plane wave with 11 transmission, 1991, and we use delay and sum to transmit the 91 transmission, and then do the limited diffraction array beam imaging use 11, 1991, and also use a square wave actual weighting. So for this we only use 187 microseconds between each transmission. So entire images can be repeated many times in a second. So in this way, we'll be able to do comparison for the same image section and almost the same moment of either heart or other organs to compare image quality between different imaging methods. So here's a result you can see. So this is image results with limited diffraction array beam imaging with square wave actual weighting with 11 transmission, 19 and 91. And this one with still the plane wave, 11 transmission, 19 and 91. And with conventional focus beam, if you focus in narrow strips and then use the interpolation to expand it into 90-degree sector, it will be very fuzzy. And if you do this, and with 91 transmission, it's quite good, but 11 is quite poor. And below is the ECG. So if you see the loop, it will be looking like that. That it's a beating heart of a human subject. In addition to the study I just have shown you, we also have done more studies on this high frame rate imaging method. For example, we also applied square wave weighting, actual weighting in the reception site, as well as use a high frame rate, apply the technique to high frame rate blood flow velocity vector images. And also we could rotate the axis in the receiving actual so that we can reduce the computation, further reduce the computation in image reconstruction. And also study the trade-off between echo densification and image quality. That means we can use different echo density to do the interpolation to get different image quality. It's a trade-off between the amount of image reconstruction time as well as image quality. And I use high frame rate imaging with divergent beams in transmission. As I mentioned, it can be, say, 15 degrees. And I also study effects of masks on superposition of reconstructed images to be, that result is to be presented later in a few weeks in Germany, and so on. So in conclusion, we have developed a high frame rate imaging system that is a Fourier-based method for pulse echo medical ultrasound images. and which is a net alternative to the conventional delay and sound imaging method for high quality and high frame rate imaging with less computations, and will be more easily to obtain a diagnostic information that is contained in the Fourier space, which might not be necessarily presented in the time space, and is likely to have an impact on the future of the pulse echo ultrasound imaging. So we have get help from many peoples, as well as funding agencies. Thank you very much.
Time for one question, George.
Well, I was wondering what the trade-off is with aperture size. If you made a much bigger aperture somehow, or multiple apertures simultaneously, that might reduce the speed, reduce the time requirement.
If you have multiple aperture for the hospital use, it's not convenient. First, the technician have to operate the two transducer, and also limitation by the human anatomy because you have bone restriction. Some places are opaque to ultrasound.
Thanks again.